Today we are going to explore one of the most fundamental concepts in calculus, which is the derivative. To understand what a derivative is, let us start with something familiar, like driving a car. If you drive a distance of 100 miles in 2 hours, your average speed is 50 miles per hour. But your speedometer does not tell you your average speed over the whole trip. It tells you how fast you are moving at one exact split second. That instantaneous rate of change is precisely what a derivative measures. Geometrically, if you have a curve on a graph representing a function, say f of x, the derivative at any given point is the slope of the tangent line that brushes right against the curve at that exact location. To define this rigorously, we use limits. If we take a function f of x, its derivative, denoted as f prime of x, is defined as the limit as h approaches 0 of the fraction, where the numerator is f of x plus h minus f of x, and the denominator is h. This fraction calculates the average slope between 2 points separated by a tiny distance h, and the limit squeezes those 2 points together until they merge into a single point. Let us look at a few mathematical examples to see how this works in practice. Suppose our function is f of x equals x squared. Using the power rule, which states that the derivative of x to the power of n is n times x to the power of n minus 1, we find that the derivative of x squared is simply 2 times x. If we evaluate this derivative at the point where x equals 3, we get 2 times 3, which equals 6. This means that at the point where x equals 3, the slope of the curve is 6. Let us try another example. Consider the function f of x equals x cubed plus 4 times. To find its derivative, we take the derivative term by term. The derivative of x cubed is 3 times x squared, and the derivative of 4 times x is just 4. Therefore, the derivative is 3 times x squared plus 4. If we want to find the rate of change when x equals 1, we substitute 1 into our derivative expression, giving us 3 times 1 squared plus 4, which equals 7. Finally, consider a constant function, such as f of x equals 5. Because a constant function is a completely flat horizontal line, its height never changes as x changes. Therefore, the slope is always 0, meaning the derivative of any constant is 0. Whether we are tracking the velocity of a moving object, calculating marginal costs in economics, or optimizing error functions in machine learning, derivatives provide the essential mathematical language to measure change at any exact moment.